You can see my slides, right?
Yes.
Okay. So, if you remember, in the last class, we were, you can hear me, right? All unmuted and everything? Yeah. Okay.
Everything is perfect.
Okay. So, in the last class, we were discussing about conductors, capacitors. We also discussed about multipole expansion and things like that. In today's class, it would be mostly on Laplace equation, how we can solve Laplace equations and find the potentials, and from there find fields and things like that. And then we would also talk about how image charges can make it very easy for us to find potentials and fields and forces in a charge distribution. Okay, so we'll read about when this is possible, how to use this image charge concept. So we'll discuss about that, and finally we'll also talk about Biot-Savart's law. Okay, so as in all the sessions, we would first talk about some concepts. We try to solve some questions, and I would try to solve the doubts that you have. Okay, so to start with, let me tell you about Laplace equation, right? So here you can see that this is Poisson's equation, right? When you have some charge, like volume charge density, you know that the potential is related to volume charge density as del square V equal to minus rho by epsilon naught. So that is Poisson's equation. Now, when rho is zero, what happens is we get this, right? So this is called Laplace equation, as we know. Now, what we'll try to do is we'll try to see what are the basic characteristics of functions that satisfy this Laplace equation. Okay, and what does it tell us physically? So, what this is telling you is that if B satisfies the Laplace equation, then at any point x, V is actually the average of the neighboring points, right? So if in one day it would look something like this, right? So plus a and minus a on two sides of x. In 2D, it would look something like this. So if you have a line integral over over a surface, over a a line that is enclosing some surface, and then if you divide by 2 pi r, so it's around a circle, and then you divide by the total circumference of the circle. So what you are getting in 2D is actually the average potential, right? And so in a way, this tells us that we if we have a suppose if you have some charge, okay, and then this is some sphere, right? So what this is telling us now, this is in 3D because I'm talking about sphere. So basically what it's telling you is that now the field or the potential because of this charge, right? Not field, potential, because potential is satisfying the Laplace equation. So if you have some charge q outside, maybe some metallic sphere, okay, and you say that what is the potential at the center, if you want to find, you can find it very easily, right? And at the same time, what you can do is you can try to find this, right? So this is potential at each point on the surface of the sphere divided by 1 by 4 pi r square. So it's basically an average over potential over the sphere. It's the surface of the sphere. And if you do that, you would see that both values are exactly the same. So that means the average potential over the sphere, any particular radius r, which encloses some point p, would be equal to what the field discharge produces at this point p, right? Considering this to be the center of the sphere. So this is a very strong point because that means you can see that if you know the potential at the center, somehow you know the average value over this entire region. And another thing that comes up from this from the first point is that Laplace equation tolerates no local maxima or minima, right? So what that means is that if there was some maxima or minima, then at any point it would be so suppose if there is a maximum, that means it's greater than whatever is there on the either side, and it's not, and it cannot be the average in that case, right? So from the first point, we can say that Laplace equation tolerates no maxima and minima. So if you have some charge q and then there's some potential, so whatever is inside, so there can be no maxima of potential inside, right? So all maxima and minima, whatever happens, should happen on the surface that encloses the region. Anywhere in a region where Laplace equation is satisfied, it can have no maxima or minima. And we'll see that it's very important in terms of, so when we will be using the image charge concept, we would see that how this concept, this mathematical concept, and can be interpreted and can lead to uniqueness theorem, which again helps us to understand why we can use this image charges. Okay. So now these are the general characteristics of harmonic functions which satisfy Laplace equations. Okay. Now what we'll try to do is we'll try to look at how one can solve Laplace equation. So suppose like these are standard questions. So first I would like to ask that are you well acquainted with how these things are done? Then I'll go fast. Otherwise I'll discuss like one by one, line by line. Hi.
Actually, I didn't watch the videos yet. So if you go in normal phase, that would be better, not in a faster phase.
So if so what I mean is that see, I can go line by line through the derivation, and I can also skip certain parts depending
Yes,
on
that's fine.
whether you are well acquainted with this ways of solving Laplace equation using partial different derivatives and things like that. So what I'll do is I'll discuss, and then if you have any doubt, you can ask me. So basically, so what we are trying to do is, see, we have two infinitely grounded metal plates, okay? And they are in the xz plane as it is mentioned. And we know that in y equal to 0, v is 0. Again, at y equal to a, v is 0. And in this strip, okay, it encloses an infinite strip which is insulated from these two plates, and that is maintained at a constant potential of v naught, right? So now we want to find the potential inside this slot, so somewhere here, and where there are no charges, right? So that satisfies the Laplace equation. So now basically, as you can see, that the configuration is independent of z. So whatever is happening, so this is along y, okay, and the plates extend along x. So in a way, it's independent of z. So what we have to solve is a two-dimensional Laplace equation. And the boundary conditions which comes from the question is the following. So v equal to 0 when y is 0, v equal to 0 when y is a, v equal to v naught, some constant value, which so at x equal to 0, okay, and v tends to 0 as x tends to infinity. So now when you have this boundary conditions, what we'll do is we'll try to define some v and see what are the conditions that has to be imposed on that v so that these conditions are satisfied. Okay. So the first step is, because now you have v is a function of x and y, right? So you have partial derivatives involved. So what we'll do is we'll try to write the function as a product. Okay. Product of so x, which is function of x, and y, which is function of y. So if you put that in this equation, you get something like this. Okay. And because we want to make this terms independent of, like, so this term we want to make it independent of y. So we don't want to have y here, and we don't want to have x here, right? So what we do is we divide by v, which is equal to xy. And this is what we get. So here the first term is solely a function of x. The second term is solely a function of y. Okay. So this is how you can write it in general. Now, if these two conditions has to be satisfied, and as you can see here, that for this to be, the the only way this could be possibly true is because is that f and g must be constant. Because so if fs f, which is a function of x, is changed, then, and keeping y fixed, and then and the vice versa. So in a way, always this condition has to be satisfied. So that means that individually this should be constant, which satisfies this condition. So if this is a constant and this one is also a constant, then this should actually satisfy this condition. So that means one should be a positive constant, other should be a negative constant. So here, as you can see, the constant is taken as k square, and we'll see why is it relevant, and like why it's taken is because it makes things much easier to solve, and we'll see why. So now one equation that we have to solve is this. Another equation that we have to solve is this. So if you do that, this is what you get, right? So that means V can be written as a product of these two functions. Now, which one to take as positive and which one to take as negative depends on the problem that you have. So here, as you can see, you have the potential as 0 both at y equal to 0 and y equal to a. So if you take an exponential combination like this, you won't be able to satisfy that condition, right? So that's why you take this. So you take minus k square so that you end up with a sinusoidal and a cosine function. So now if you do that, what you get is this. So this is the general form of V. Okay, when you have a equation like this and a problem like this. So now what you do is here, if you put the condition 4, right? So the fourth condition says that as v tends to 0, x tends to, like, as x tends to infinity, v tends to 0. So if you do that, that tells that what you can do is okay, that means this term should go away, right? Because it's an exponentially increasing function. So if you have this, you will never be able to reach v equal to 0 as x tends to infinity. So this a should go away, right? So this is what is being done. And because b is a constant, you can take it and absorb it within c and d. So this is what you end up getting. Now here, again, if you put condition 1, you would see that you need d to be 0. So what is condition 1 is this. So v equal to 0 when y is 0, right? So that means this value should go to 0 because cos 0 is 1. So d should be 0. So this is another. So gradually, as you are imposing the conditions, your potential is taking up a form, right, which satisfies the boundary conditions. And now, as you can see, that we saw that when y equal to a, it's 0, right? That means, and it can have all possible values of, like, ky can have all possible values where k is equal to n pi by a, right? N are the integers. So that means all this values where k is given by this term and n can vary from like all the integral factors. So all of this satisfy the first, like this three condition 1, 2, and 4, right? But now you also have to satisfy 3, which says that the potential here is v naught, and that's constant, right? And that's some function of y. So if you have to do that, that means now all of them individually are satisfying Laplace equation. So what we can say is the linear superposition or linear combination of these functions will also satisfy Laplace equation. So what we write is this linear superposition of all the different solutions that satisfy the conditions, right? And now we say that when x equal to 0, we get this term, and that should be equal to v naught. This is the third condition that we are imposing on the potential expression. Now here comes an important trick that we have to use, and this is something which we'll be using in all this type of questions, is the Fourier trick. So this is a sinusoidal function, and we know that the sinusoids can form a complete set, right? And they have this orthogonality property. So this will be used, and what we do is we multiply by this integral on both sides, okay? And we know that, so this orthogonality property, what it does is it simplifies the calculation on this side, and that provides us with the value of this constants, like all these constants that were there in this expansion. So now this is what you get. So you know the individual constants, which are like for each values of n, okay? And as you can see in this question, when n is even, it's 0, and when n is odd, you get some non-zero value. So that means your expansion, like the series of solutions that make up the potential, that will only have values where n is odd, right? So from here, now we have reached to this expression for the potential. So it's important that whenever you'll be solving these questions, these two properties of this function. So as you can see, in general, you are writing any function, which is suppose this potential, in terms of some other functions, like here the sinusoids, okay? And these functions, this f and y, they should form a complete set, and they should have some orthogonality property, as you can see here. So because we'll be using that to reach to the expressions for the constants or the coefficients of the terms, right? So that's how we generally solve Laplace equations, and this is what we get. So for this problem, this is the potential that we are getting, okay? Now that we know the potential, if we go back to this question, so now we know how the potential looks in this region, right? So the next part of the question says that what would be the surface charge density at y equal to 0. So this is an infinite strip, right, which is at a constant potential. So if you consider that to be a conducting, like insulated conducting, not insulated conducting, some conducting surface, and then on which is insulated from this two plates. Okay, so it's not grounded and it's at a constant potential V naught. What would be the surface charge density at y equal to 0? Right? So that is the second part of the question, which says that determine the charge density on the strip at x equal to 0. So that means this plane, like this at this point, and we want to find how it changes as a function of y. So what we then do is, so this is your potential, right? This is what we just derived. So now that we know potential, we have to find the charge density. So can you tell me what should be the relation that one should use in this case? So there should be a relation which relates charge density with potential. And what is that? Any idea?
Capacitance.
Anybody, any idea? I'm not able to.
Capacitance.
Hello? Yeah. So Lakshmi, are you telling something and I'm unable
Yes,
to
yes.
hear?
Is it
Yes.
capacitance relationship?
Like which relation are you talking about?
Like I'm thinking of the relationship of capacitance here,
Uh,
but I'm
I
not
don't
sure on this one.
I don't know which relation exactly are you talking about, but what we have to look at is, potential, and you have to go to charge density, right? So is there a relation that relates? Okay, so first
Just now we saw something about the Poisson, right? Poisson equation that
okay.
is related to the charge density. Maybe we could try that expression, or we can expand this equation and find the del V square component and equate it to charge density.
Okay, see, this potential value that you got is for the points that are inside the inside that metallic like insulated region, right? Now from here you have to reach to like the, so how do I explain? So you got the potential in this region, you know that the potential in this region is constant, you want to find the charge density along, like as a function of y when x is 0, so along this line, right? So what I mean now is, you know the potential here. So in a way, what you have to do is you have to find the relation that relates potential with sigma, or you can try to think of the relation that relates electric field with sigma, and then go back to potential from electric field. That will also do.
Okay.
So what is the relation that relates electric field and sigma? Suppose if you have some surface, okay, and there is some electric field above, some electric field below, and how is it related to the charge density on the surface?
J is equal to sigma E.
Sorry.
J is equal to sigma E.
Okay. So it's like E equal to D equal to sigma. No, what did you say?
J is equal to sigma E. Current
Sigma.
density is
Current density. Acha, J is equal to. Oh, no. So, like suppose what I mean is, how I can just tell you the answer, but I don't want to tell. That's the thing. So the thing is that how do you maybe so when we talk about the components of electric field, okay. So suppose if you have some conductor, okay, and how do you say that what are the boundary conditions at the conductor surface? And when you write it about maybe the normal and the tangential components of electric field, what do we say? That the tangential components are continuous, right? So below and above, E, E, E tangential will be equal, right? And what would happen to the normal components? So the normal components, suppose if your surface has some surface charge density sigma, then there'll be a discontinuity of sigma by epsilon naught, right? So in a way, E above minus E below can be written as sigma by epsilon naught, right? And if there is, so if it is a conductor and there is no field inside, so in a way you can write it as, so what I mean is, in that case, E will be equal to sigma by epsilon naught outside, right? Is that clear?
yes.
Right. So now if you know electric field and you know the relation between electric field and potential, right? So from here, what you finally get to is something like this, right? Sigma by epsilon naught will be equal to E, and E we know is equal to minus grad V, right? So you can write E in terms of potential by this derivative. So this is the relation that relates potential with sigma. Clear? So now that you have this potential, you can find the derivative, right? And if you do the derivative, obviously your normal will be in the x direction, right? Because you have the surface and you want to find. So the derivative here, n means x. So if you do that derivative, you get this expression, right? So this is your expression for the surface charge density, right? So anywhere in like there are questions in your assignments or in whatever questions that you have, if you have to find the surface charge density, you can do it by two ways. One thing is you find the potential and you use this relation, okay, with the correct sign of n cap and things like that. And other thing is you can go from potential directly to electric field, okay, and there use that boundary condition, E above minus E below equal to sigma by epsilon naught or sigma by epsilon if you have some dielectric, right? So depending on that, you can find the surface charge density on some surface if you know the potential. Okay. So now this is another question. Here, what is different here is that now you have something in like some what do I say, symmetry in X. So what it means is that plus B and minus B, plus X and minus X have a symmetry, right? And that would come up in the expression. So these are the boundary conditions, just similar to as we were solving in the last case. And now this is the general form, right? But here, now we have this added, like if we look at the boundary conditions, we know that there's a symmetry about X. So what does that tell us? How should that affect the constants? Can anyone tell me? So we know that the function looks similar in X and minus X. So what does it tell us about A, B, C, or D? Basically, we are finding potential somewhere inside, and we know that these two surfaces are at zero potentials and these surfaces are at V naught potentials. So see, because it's symmetric about x, that means a and b should be equal, right? Because x and minus x, if you replace x by minus x, it should be same. So that means a and b should be equal, right? So if you do that, into c and d, and this is the expression that you get. So this is by making use of the fact that your potential, like your system has a symmetry about x. Okay. Now what we do is we apply the other boundary conditions. So again, if you apply the conditions 1 and 2, what you get is d should be 0 and k, for in all values of k equal to n pi by a, your condition gets satisfied. So this is the expression of potential that you get, right? So now, because your function is symmetric about x, if you satisfy this condition will automatically be satisfied. So somehow now you have to say that, so all values of v for any value of n is satisfies the Laplace equation. But now we have to look at some combination of those functions which satisfies the third condition, right? So that's why we write it as a series of all those functions. Okay. And we say that at x equal to b, it should be equal to v naught as given in our problem. And now, if you again use the same Fourier trick that we did, we would get something like this. So this in a way tells us the expression for the coefficients that we have in the expression. So from here, we can write the potential, and this is how the potential looks. Okay. So this is another question. So before that, till this, it's clear, right? I'll assume that it's clear because this is same as we were doing in the last case. Now, this is another question where now you also have to consider z. So why this is interesting is because now you have to change your constants in a way because you have another partial derivative here, right? And these are the boundary conditions that has to be satisfied according to the question. So you can see that these are v equal to 0 surfaces, and this is a v equal to v naught, okay, along y and z. So it's in a plane now, and these are the conditions. Now, so it's important that whenever you are given some question, try to clearly write the boundary condition. That would solve most of your confusions. And now what it tells you that now you have to write it as a product of three functions, x, y, and z. Okay. And so if you divide by v, you would get three terms, which would be independently function of x, y, and z. And each of them have to be constant such that c1 plus c2 plus c3 is equal to 0. But now, how do we define c1, c2, and c3? We cannot just write it as k square and minus k square, right? Because there's a third constant that's there. So what we do is we include another term, that is L. So we write the first constant like c1 as k square plus L square, c2 as minus k square, c3 as minus L square. And whether like which would be taken as positive and which others will be taken as negative depends on your question. Okay. So as seen here, you can see that in y, along y and along z, there is a, so it's 0 at y equal to 0 and y equal to a. It's 0 at z equal to 0 and z equal to b. Now, for these conditions to be satisfied, you can just look at it and say that there could be, so it could be a sinusoidal function, or it can be all kinds of sinusoidal functions where k is given by n pi by a along y and n pi by b along z, which satisfies this condition that it should be 0 at. So all those multiples, right? All those multiples of sinusoids would give you a solution for that. So that means this should be like this coefficient should be taken as negative for this question. So that's how you define your constants, and this is the general form of x, y, and z that you get. Okay. So now, if you remember this boundary conditions and you try to impose them on the general form one by one, you would finally get to, so this is some expression, and then you write it as a combination of all those possibilities. Okay. And then you say that at x equal to 0, it should be equal to v naught, right? As given here. And here now again, you have to use the Fourier trick, but here you have to use two such integrals because there are two summations involved. So you multiply by this term n prime and m prime, okay? And you use the orthogonality relations. So this is how you reach to the coefficients that should come here, right? So if you solve it, you see that only for n and m being odd, you get a non-zero coefficient. So that means v of xyz should, okay. Okay, so v of xyz should look like this, right? So this is how it's similar to the two-dimensional case, but this is how you have to just remember how you are defining the constants and how you are dividing how you are, separating the variables, right? This is at the first place how you are separating the variables, writing the function as a form of products, and how you are choosing the constants, putting the proper boundary conditions, using the Fourier trick to find the coefficients, and that's how you reach the potential. Okay. Now, this is another question which is similar to the first question that we tried, but here what is being told is that the potential is not all throughout constant. From 0 to a by 2, it's v naught, and from a by 2 to a, it's minus v naught, right? So if I go back to the last question, the similar type of question that we did at first, what should change? Like this is the question that we solved, right? And here v naught was, like this was v naught, which is a function of y, and somehow and we used all these relations, we get to the expression for potential, right? So in this entire solution, now you know that this is from 0 to a by 2, it's v naught, from a by 2 to a, it's minus v naught. So how do you implement that in this solution? What should change, or where should you implement it? Any idea? Just look at the solution and try to think that some things would be common, right? Some steps would be common, but somewhere you have to include that condition. So where should we do that?
Can you show the question, final question?
Okay. One second. So this is the final question.
Okay.
So we solved a similar question where it was said that in this strip, v is given as v naught, which is some function of y. Now you have some function defined which says that for y equal to 0 to a by 2, it's v naught, and from a by 2 to a, it's minus v naught. So where do we use this information in order to reach the potential, right? So if I should I go back to the expressions, or do you want to solve it? So try to think of like the steps. Okay, I'll go back so that you can relate what's happening. So if you look at this place, this condition is true, always true, because we are finding the potential somewhere here where there is no charge. Now in this condition here, it would have a you would have an expression. So it should be v naught while y ranges from 0 to a by 2, minus v naught while y ranges from a by 2 to a, right? And now you have this kind of, so you write the potential in terms of products, you do this separation of variables, okay? All this constants, everything, you put this. So this thing should remain identical, right? Because what you are doing is, even now we know that it should get to 0 as x tends to infinity. So a should go away. So that condition is still true. Okay. We know that d should be 0 because then your this condition won't be satisfied. So till this it's still true. We know that k is equal to n pi by a because why? Because at this condition is also true. At v equal to 0, y is equal to a, right? So v equal to 0 when y is equal to a. Yes. So from here, we know that this condition is also true. Okay. So that means this expression is correct. We write it, this is just writing the linear superpositions of all the possible functions, right? Now here, what you are doing is you are writing it for some function of v naught, some function like some potential v naught, which is function of y, right? And you are solving it. So nowhere here you have actually used the form of v naught, right? So this is for any general form of v naught that you can get as a function of y. And this is how the coefficients look like. Okay, it's in terms of v naught, and these are so this integral will give you the coefficients. So what is changing in this current question is that now you have the form or the functional form of v naught. So what you have to do is you have to put the value of v naught so this is an integral, right, for 0 to a. So what will happen is from 0 to a by 2, this will be v naught. From a by 2 to a, it will be minus v naught, right? So now you are actually using the functional form of a potential. This is for any general function of potential, which is a function of y specified. So now when you use that, you can get an expression for Cn. And that expression will obviously change now depending on this, right? So this integral will change and that will change your potential, right? So let's see if we do that, what do we get? Okay. So here, this was the general form. Now, in this case, this is your potential. Now you put that form here. And if you solve that, this is the expression for the coefficients that you get, right? So this tells you that now the coefficients are, so it would be 0 if 8 is odd or divisible by 4, and otherwise it would be 4, right? So from there, you can write the expressions for the coefficients for different values of n, and that would give you the potential for this problem, right? So this is how you have to use the functional form of potential if it is specified at the boundary. Is it clear? Right. Okay. So all this we were doing in the Cartesian coordinate, we can do it in the spherical coordinates. So there we have now written the Laplace equation in spherical coordinate. Okay. And as you can see, if we have azimuthal symmetry, we can get rid of this term. So then this is what we end up getting. Again, here you have to write the potential. Now the variables are r, theta, and phi. Now, if it has azimuthal symmetry, this will go away. So then v is function of r and phi and theta, right? And you have to write it as a product of these terms, which are independently function of r and theta. And then if you do that, you divide by v, similar process, same as the other, the Cartesian form, only now the variables have changed and the expression has changed. So now this term is solely a function of r, this is solely a function of theta, okay? And that means this has to be some constants. So you can write it as this. Now, why have you chosen this particular form of constant? We'll see that this is very useful in solving. So basically it's some constant, but we see that this makes our solving the question easier, and it's actually valid. So the constants always have some form like this. So this is some constant, and this is minus of that, so that when you add it, it becomes 0, right? So now you individually solve this equation and this equation. So when you solve this equation, this is a general form of r that satisfies this equation, okay? And if you solve the equation for theta, you see that this so the Legendre polynomials satisfy this equation, okay? So these are some, so this Rodrigues formula in a way tells you how the Legendre polynomials looks like, okay? And Again, here the Legendre polynomials will have some orthogonality relations which will be used in order to reach the coefficients, right? So in a way, now what this tells us, so what this tells us is you can write V as a series of functions where each can, so this is the radial component, the radial part of your of the potential, and this is the theta dependent part, right? And it is actually a Legendre polynomial. And so now you can have all values of L, and which values survive depends on the question and the boundary conditions. So now this is a general form that one has to use when you are in the spherical system, the spherical coordinate system. So suppose here, if the potential is specified on the surface of some hollow sphere of radius r, and it is given as v naught, which is some function of theta, so how would the potential be inside the sphere, right? So again here, what you have to do is, you remember this is your general form, but now what you are finding is something, so the potential inside the sphere. That means your r value can go to 0. And if you have this term, then if r goes to 0, this term will blow off, right? So you cannot have this term. So whenever you are doing it inside the sphere, your BL terms will go to 0, and you'll only have the AL dependent terms, right? So this is how your potential should look like. And now you know that at r equal to capital R, your function is specified. You know the potential. So this is the expression. Again, we'll be using this orthogonality relations of Legendre polynomials in order to derive the constants. Okay, so this is the coefficient or the constant. Okay, and if you now know the coefficient, you can put it here, and that would give you the expression for the like, if you can put it here, and that would give you the expression for the potential for any point inside the sphere. Okay, and we'll see that. So let's see an example and see how this can be used. So suppose you know that your potential is this, right? So some function of theta. So that means the potential on the surface of the sphere is specified, and this is some function of theta. You want to find the potential at any place inside the sphere. So based on what we just discussed, can you tell me how to proceed with this question? So you know this. What do you do next? So what should be the aim? You have the potential. You want to find the on the surface. You want to find the potential inside the sphere. So what should you look for? What do you need? So for any points inside the sphere, this is how the potential looks, right? So for all values of L from 0 to infinity, we know the functional form of PL cos theta, and this is just r to the power L. So what is unknown and what defines the expression or the potential expression is this coefficients, right? So we want to find the coefficients, right? And how do we do it? We know that the potential at R, like at R equal to capital R, would look something like this, right? So here, this potential, which is already provided to you, if you write it, expand it, you can write it as some function of Legendre polynomials, right? And then if you compare it with this form, you can say that here your A naught is k by 2 and A1 is minus k by 2R. So now if you know the coefficients, you can actually just put the coefficients in this expression, and that will provide you with the potential at any point inside the sphere. Is this clear? Okay. And now how will the things change if you have to find the potential outside the sphere? So how will the functional form of potential look like at the first place if you are asked to find the potential outside the sphere? Any idea? So this is the general form, right? This is the general form of potential. We said that when we are inside the sphere, your R can go to 0, and then this term would blow off. That's why we cannot have BL terms there while we are finding the potential inside the sphere. Now, what happens when you want to find the potential outside the sphere? Which terms should remain, and what should be the expression looking like? So your potential should never diverge. It should never be, it should never blow off. So when you're outside the sphere, what could be the value of R's? How does your value of R range?
R can be up to infinity from
Right?
the radius of sphere to
To the
to
infinity, to
maximum possible.
infinity.
Yeah, to infinity.
Right, right. So which term should remain, and what should, like, how should this expression be modified so that the potential does not diverge? So if you put R equal to infinity, what happens to these terms?
Um, B divided by R power L plus 1, that will become 0.
Right? And what would happen to this term? So something like R to the power infinity, right? Infinity,
Yes.
like a into infinity to the power L. So that scales as like it will go to infinity, right? So you cannot have this term,
Yes.
right? So just like inside you cannot have the BL terms, outside you can't have the AL terms. Okay. So there you have to have some expression like this, right? And then depending on how your potential is specified on the surface, you can again use the similar process, and that will provide you. So if that will provide you the coefficients BL, okay, and you can put that in order to find the potential at any points outside the sphere. So this is a general way of solving the Laplace equation and finding the potentials. So there are very standard questions which you can solve from books like Griffiths and many other books, Jackson and anywhere. So these are very standard problems which you need to practice. If you don't practice, you won't be able to get hold of this. Okay. So in if I have to summarize this thing, what it is telling you is that you will have some boundary conditions given at some surface which is enclosing some volume, okay? And then you want to find the potential somewhere inside the volume or somewhere outside, and where there is no charge. So where Laplace equation holds. So then you have to use the Laplace equation to find the potential in that area, in that region. And then if you find the potential, you can also find the electric field. How do you do that? By using this relation, right? Minus grad V. And now if you know E, you can use this relation to go to to find the surface charge density at any surface. So now just for your you know just as a concept, suppose if you have some surface like something like this, okay, and the electric fields are directed somewhere in this direction. So you have some plane maybe here and some plane here, okay, and you know the potential at this end, you know the potential at this end, so you can also find the potential which is there in between these planes, right? And effectively you can also find the electric field. Now and once you find the electric field, you see that the electric field is directed in this direction, okay. So now that you know this, if you are asked what should be the charge density on this plate or what should be the charge density on this plate, how do you solve it? So what you do is, see, here you know that the electric fields are directed in this direction, right? So you can use this relation, okay. So anywhere outside, the electric field is 0, and then here the electric field is directed in this direction. So you can say that for this surface, okay, so you have the E below term, right? So the E below term persists. Okay. And what would be the n cap direction? The n cap direction will be along this, right? Sorry. Okay. I don't know how to. Okay. So the n cap direction will be 1 second. Sorry.
Normal to the plane
Downwards,
inwards,
right?
inside the plate. It's downwards.
Yes, exactly. Downwards. So now if you use that relation, what happens is you have some minus E below equal to sigma by epsilon naught, where n cap is also directed downwards. Okay, so your minus signs will get cancelled, and somehow if you know the electric field, if you multiply by this by sigma naught or sigma, if you have some dielectric, you can find the charge density on the surface. Similarly, here what would happen is your E above remains, your E below is 0. And what happens is in this place, now how will the n cap be directed? It will be directed upwards, right? So if you use that relation, again, you can find the, you know E already. So you can find the sigma on this surface. And as you can understand, if the fields are directed from this point, this will have some positive charge, right? And this should have some negative charges, because fields emanate from positive charge and go towards negative. So this is how in general you can use these relations in order to find potentials, fields, or charge densities, right? So is this clear to everyone? So I guess similar kind of questions can be there in your assignments, so you can use these concepts. Okay, right. So now what we'll move to is uniqueness theorem. Okay, and this is very much at the heart of the concept of image charges that we will be using. So as we saw that Laplace in Laplace equation, so it supports no and it actually comes from that point that what the first uniqueness theorem is telling you. Yeah, I'll change to pointer. So the first uniqueness theorem is telling you that the solution to Laplace equation in some volume, some volume V is uniquely determined if V is specified on the boundary surface S. So if you have a potential specified on the surface that is enclosing this volume, then anywhere inside this volume, the solution for Laplace equation will have only one unique solution, right? And why is it so? Is because suppose if you had two solutions, V1 and V2, then you know that it satisfies Laplace equation, right? So del square V1 is equal to 0. Again, del square V2 is also equal to 0. And now as it supports linear superposition, you can say that some function V3, which is given as V1 minus V2, will also satisfy the Laplace equation, right? So del square V3 should also be equal to 0. But we know that the Laplace equation allows no local maxima and minima. So all extrema should occur at the boundaries. And at the boundary, like boundary meaning the surface here, surface enclosing the volume, the potential is already specified. So the value of V1 at the boundary is V, the value of V2 at the boundary is V. So the value of V3 at the boundary is 0, V1 minus V2, which is equal to 0, right? On the surface, V3 is 0. And there can be no maxima or minima anywhere inside this volume. So that in a way tells you that the maximum and minimum of V3 are both 0. So that means V3 is 0 everywhere, which in a way tells you that V1 is equal to V2. So there can be only one solution of potential that defines the potential inside this volume when you have the potential very well defined on the surface, right? So we'll see, and this lies at the heart of why we can use image charges in order to solve for potentials and fields and forces and things like that, right? There's another uniqueness theorem which says that if you have some volume which is surrounded by conductors, okay, and if the charge density is specified on the conductors, on each one of the conductors, okay, the electric field is uniquely determined if the total charge on each of the conductors is given, okay. So if you know the total charge on each of the conductors, you can, in this volume which encloses the conductors, okay, with some charge density, you can actually uniquely determine the electric field. Okay. So now that we know the uniqueness theorem, we are asked that we have this charge q, okay, and this is a conducting surface, okay, which is at potential 0, okay, and you have this charge here. Now, what is the potential in the region above the plane? Anywhere above the plane. It's not just equal to q by 4 pi epsilon naught r. Why? Can you tell me why? Any idea? So normally if you have some charge q, you know the potential around it, right? It should be q by 4 pi epsilon naught r. So in this case, the presence of this conducting surface, what difference does it make that the potential in the region above the plane changes? How does it change, or why does it change?
Because it is a plane of charge or metallic plate, not a point.
So basically you have a conducting plate which is at some 0 potential, okay, and you have this charge q here. Now there are no extra free charges anywhere, okay, but you want to find the potential anywhere in this region, and you know that it's not trivial just equal to q by 4 pi epsilon naught r. But why so? So what exactly is this conducting plate doing that it is changing the potential in around the charge?
It is forcefully setting the reference as 0 at some point.
Okay, and
As
what's
we are
happening?
setting that at 0 potential on the plate, so the other region potential will also vary. If I do not have the plate, if it's free space, then the potential distribution would be varying at the rate of r, like divided by r. Whereas if I'm setting a reference means, then the system need to adapt to that plate, and the boundary condition here is 0 volt. So between that region, the potential will adjust itself, with
So
maximum being at q and the least
right,
at v
so
equal
in
to
a
0.
way this plate is changing the potential distribution, right? And how exactly? So if you think of physically, how is this happening? So obviously this metal plates will be having some charges, right? Some free charges in the conductor. And what would happen is, because of this presence of q, there'll be obviously some induced charges, right? So that induced charges is such that the potential in this region is actually will be different from what we would have in general, like with just a point charge, right? So now, if you think of the uniqueness theorem we just discussed, so we know that the potential is 0 at z equal to 0, right? Here in this plane, the potential is 0. And we know that anywhere far from the charge, like if it is a point charge, it will go as 1 over 1 by r. And anywhere far from the charge, again, the potential will go to 0, right? So that means you actually know the potential over the surface that is enclosing this upper plane, right? Am I clear? So now that if you know that, so if you know that, so what it means is that your potential that will be there in this first plane, your potential will be uniquely determined, right? Is that clear? So whatever will the potential be because of this conducting plate and this charge q will be same as if we can mimic this by some other ways, right? If you want to mimic this v equal to 0 0 surface in some way, so then again the potential is the definition of potential on the surface remains the same. So then by uniqueness theorem, the potential inside or potential in this above the plane in this region should be the same. So it's a unique solution. So based on that, what we do now is we replace this conducting surface and we put a minus q charge at some distance d, right? Which is like at the same distance from like so the distance between plus q, this charge that we have provided, and the plane is same as the distance from the minus q. So this is just mathematical way of easily solving this problem, okay? So we have minus q here and we have this at the same distance d, right? So what this ensures is that now if you find the potential at any plane at z equal to 0, like at any point at z equal to 0, it would look something like this in the xy plane, and that means this is the same condition as this, right? So we can just solve for this question, and we'll be able to get the potential that one can expect in this case above the plane. And this is very easy to do. So this is just like finding we know the distances, and this is how the potential should like in general look like. Okay, and if you use that, we can actually also find sigma, just like we used the relation before. So you can find sigma from there. If you find sigma, so what is the sigma? This is actually the charge density on this conducting surface, right? And if you know sigma, you can also find the total induced charge. Okay, and if you do that, you would see that it would actually be equal to minus q, right? And one can also find the force. So because of this induced charges, there'll be an attraction that this plus q charge will feel because of the induced charges. And one can find that force of attraction, and it would look like this, right? So you are basically finding the force between these two charges. It's same as doing that. However, the work done will be half, because while here you have to bring the plus q and the minus q charge from infinity to this point. So you have to do some work for both of this. Here in the original problem, you just have to bring this plus q charge. So the work done in this case would be half of what one can expect in this case, right? So this is the normal method of images, which helps us to find potentials in a much simpler way. So now this is another very simple question. You can try to solve it. I just shared the solution because this is a very standard question. So here it says that you have this grounded conducting sphere. So anywhere at the surface V is equal to 0. Okay, and somewhere at a distance A, much greater than R, not much greater, but greater than R, the radius, there is this charge Q. You say that what is the potential outside the sphere? Okay, and you would see that if you put a q prime charge somewhere here inside, okay, which has this magnitude at a distance b from the center, you would see that the potential will again be 0 on the surface. Okay, and that would mimic this condition, and you can use that to write the expression for the potential. So writing the expression for the potential at some point r outside the sphere would be same as finding the potential for this problem, and this is how it can look like. Okay, and you can also find the forces and things like that. So this is a very standard question. You can see that how this values make the potential 0 on the surface. It's a trivial thing to do. Okay, so now this is another interesting thing rather. So what now happens is initially v was equal to 0, right? But now you say that v is equal to v naught, right? So somewhere on the surface, V is equal to V naught. So what do you think? How will the image charges in this case be? And where should they be put? So how should it be different from the last case, right? And can we find the force of attraction between a point charge Q and a neutral conducting sphere? So first try to address the first question, that when V is equal to V naught as specified on the surface, how will the image charges vary from the one we just discussed in the last problem? Any idea? So in the last case, we had V equal to 0, right? So now what you have to do is you have to mimic this situation where you have this charge Q here, but now you have this metal sphere with some potential V naught. So there are two things. First, because of the presence of this Q, there'll be some induced charges that can have some potential on the surface. So we have to make that to 0, right? But then there is an additive effect of some charge, right? Which results in some potential V naught on the surface.
do we need to introduce any other plate at zero potential near this one? Or
Zero potential? There is no zero potential. So this metal, yeah, tell me. So see, there is no zero potential. So initially we had the metal sphere surface to be at zero potential. Now we have it at a constant potential V naught. Okay.
that is fine. What I'm trying to tell is, do we need to bring any other metal plate and forcefully set that into zero potential? Maybe other side of the sphere, left side of the sphere, we can put that plate, make that into a zero potential, and image this Q on the other side of that plate.
Obviously, you have to somehow. So think of, if you bring some charge, okay, how can you bring some charge and put it somewhere such that the potential becomes V naught? So suppose this is your initial condition, okay? So you know that this is your charge Q. Now, if you put Q prime somewhere here, you know that the potential is zero. Now, given that condition, is there a way that you can bring some charge and keep it somewhere so that the potential becomes V naught? Somewhere in this region. Anybody, any idea? Okay, so if I discuss, then you'll see that it would get clear. See, we want the potential to be V naught, right? So Q and Q prime makes the potential zero. We have to add another charge, okay, which makes the potential V naught. What if we put some charge at the center such that the potential at the surface becomes V naught? So we know that if there's some charge Q double prime at the center, what would the potential be? It would be Q double prime by 4 pi epsilon naught R, right? So now your V naught is specified. So what I mean is that you can, if you know some Q here, okay, you can find the potential for this Q on this surface, right? You can find that potential. Now your potential is specified. You have V naught. The Q and Q prime makes it zero. You have to add some extra potential, extra charge at the center such that the potential becomes V naught. Then you are actually mimicking this situation, right? So you know the relation between Q at the center and the potential at the surface is given as V naught is equal to Q by 4 pi epsilon naught capital R, right? So that means from that relation, you can actually find the charge. So some Q double prime charge that you have to put at the center, along with the Q prime that initially balances the effect of this plus Q, balances the effect of the induced charge and make the potential initially zero, right? So what you do is you have, one second. So you have Q prime, both of them make the potential zero. Then you have another charge Q double prime, which makes the potential V naught, right? And Q double prime is given as 4 pi epsilon naught V naught R. So is this clear? So that means whatever the question tells you, like, so in a way you want to find the potential here. So you have to maintain the given potential conditions at the surface that is enclosing your volume. So one surface is this, right? So the potential here is V naught. So somehow you have to mimic that potential, and somewhere in infinity it would go to zero. So while Q and Q prime makes it zero, you can just add another charge here, which maintains, which can maintain the potential at the required value. Is this clear to everyone? Okay. So now the second part of the question, which says that find the force of attraction between a point charge Q and a neutral conducting sphere. Okay. So what it is telling you is that now so you have some Q, okay, and that induces some Q prime charge. So that results in some image charge of Q prime here, right? Now it tells you that you have to make the conducting sphere neutral. That means you have to add some Q prime charge, Q double prime charge, such that Q prime plus Q double prime is equal to 0, right? So if you do that, you can actually use this relation. And from there, now it's just a matter of, what do I say? Just normal force, Coulomb force expression. So if you use that, you can actually find what is the force of attraction. So this minus sign denotes the attraction between the point charge Q and the neutral conducting sphere. So when you have to make it neutral, that means the extra charge that you are putting in should be equal and opposite to the Q prime that you initially put to make the potential 0. Okay. So, okay. Okay. So now let us use this concept of whatever we just learned about image charges. So here we have this two grounded conducting planes. So the potential along this plane and this plane is 0. Okay, and they meet at 90 degree. You have some charge Q here. So how should the image charges be located and what should be the potential like? Okay, and then we'll gradually go to the other subsections. So what do you think? How should the image charges be distributed? This is a very standard question. So somehow you have to put some charge so that the potential remains 0 here, right? So that means you need to put some minus Q at some equal distance from this end, okay, so that it becomes 0. Now, when you have that extra minus Q charge, you also have to have this surface to be 0, right? So that means you also have to have something like Q at this end. And again, to balance that and make the potential 0 along X, you have to have this minus Q. So this also balances the 0 potential, like maintains the 0 potential along Y. So this is how the image charges should get distributed, right? And if you know this, you can actually find the potential by just finding the distances between the different charges. Okay. Now, what's the next part of the question is that if the angle was not 90 and something else, is it still possible to solve the problem by the method of images? Okay. And if not, when not and why not, right? So suppose if you think that the angle between these conducting plates was 45. Okay. So how can you do the charge distribution? So this is your given plus Q charge, suppose. Okay. And you want to find the potential in this region. So what you do is now, so basically this is your given charge, right? So in order to keep it balanced along X, you first put a minus charge here. Okay. Now along the 45-degree, you have to maintain it, right? So because of that, you have another minus charge on this side. But then this will also have an effect on this, right? So in order to balance that, you have another, so that the potential still remains 0, you have to bring this third plus charge here, right? And similarly, this plus charge here. And same ways, again, because of this, you need to bring another charge here. Okay. And then if you have to maintain the potential around the 45-degree, maintain the potential to 0, you need to bring another plus charge here. Okay. And this is how the distribution should look like. Basically, you are just doing like looking at one charge and looking at the effect of all the other charges and how to maintain the potential 0 at the two ends, right? So for 45-degree, as you can see, this is possible, right? And if you look at both of these questions, you can see that the number of images or number of image charges that is required is something like this, right? So here you needed three image charges, right? This was your given charge, right? And it was 90 degrees, so 360° by 90 minus 1. Here you needed actually 7 charges, like this was your given charges. So it's like 1, 2, 3, 4, 5, 6, 7, right? So it's 360° by 45 minus 1. So this is in general how the number of charge requirement is. Now what happens if you have theta equal to 135, right? Some random value 135. What you see is here in this case, it does not work. Why? Because this is your given charge. Okay, so because of that, first to maintain the potential to be 0 along this line, you put this minus charge here. Okay, but you also have to maintain the potential along this line. So because of that, you put this minus charge here, right? And now to again maintain the potential 0 along this line, what happens is you bring this plus charge here. But the problem now is that this plus charge that you have brought, this charge lies in the region where you want to find the potential. So this is a very important point for image charges, is that you cannot put the image charge in the region where you want to find the potential. What you are doing is you are mimicking the situation such that you can result in a case where the potentials on the surface enclosing the volume remains same as your as the given system. Okay, to some simpler form using some image charges. But if the image charges comes in the region, that means your actual situation gets changed. So you cannot have potentials in the region where you want to find the field or the potential. But for certain values of theta or certain values of angles between the surfaces, there is no other way but to bring this charge here, and so this method fails in that case. So not for all values of theta will this method work. Okay. So when will it work? So basically this will work for all values of theta, which will be an integral divisor of 180 degrees. So something like 180, 90, 60, 45. Okay. But not like 135. Okay. Because of this reason that we just discussed. So for certain values of theta, where theta is the angle between these two conducting surface, we can use the image charge method. Okay. So now, if you go back to the last question of where we had this 90° between the two conducting surface, and here it says that we have this plus q charge symmetrically placed at distance d, okay, and we want to find the net force on the charge. So what would happen is this charge would induce some charges on this metallic conducting plates, right? And so there'll be a net force, net attractive force that it would feel. So what would be that force? So what would be the magnitude of that force? And how do you find that? So what we do is we replicate, we somehow mimic this situation, right? So we get something like this. Now for all of these charges will individually exert some force on Q, right? This will pull it this side, this will pull it this side, and this will have a repulsive force F3. Now F1 and F2, as you can see, the resultant will be somewhere along this line, and then F3 and the resultant of F1 and F2 are in opposite directions. So that would provide you with some effective net force value. So can you try to solve and tell me what the solution will be? It's normal Coulomb law question now. So as you can see, F1 and F2 should have same magnitudes.
Should be option B or C.
Okay. Now, why does this or come in the answer?
I saw the direction of forces F1 and F2. I assumed F3 would be inwards, and the first two options had away from the corner, right? So A and B
Right.
had that option, so I excluded that two things.
Okay. Very good. Correct way of thinking. But then, uh, just it's a normal question, right? So you have this distance as 2d, so it's q square by 8d square. That should be this force, right? And again this, but you will have some component along this direction of theta equal to 45. So if you put that, and then you can see that F3 is in a direction opposite to the resultant of F1 and F2. So if you subtract, so you would get something like this. So this is your F1, F2, this is F3, this is the resultant of F1 and F2, this is this is the net force. So you actually subtract the, so you have to subtract F3 from the resultant of F1 and F2, and the resultant force would be towards the corner. So this in a way tells you how simplified the questions become when you use the this image charges, right? Okay. Now here, this is another question where you have 2 point charges placed at some distance from some infinitely grounded conducting sheet in the xy plane. Okay, and it says that at a point z, which is much greater than this distance d, which specifies the charge distribution, uh, how should the electrostatic potential look like? Okay, so it's something like this. So because it's an infinitely grounded conducting sheet, so you can think of how the image charges will be. It should be something like this. But now that you know that this is your this is how your system is, so what do you think the electrostatic potential of this charge distribution should be approximately at larger distances? So how to address this question now? You you have done the image charge, suppose, and now how to address the question?
Can we summate this charge minus q and 3q?
Can you?
Can we represent this minus q and 3q in a position between d and 2d such that it replicates the effect of these two charges?
Sorry, I did not get you.
Like
What?
we have two charges here, right? Minus q and 3q along the
Hmm.
z-axis. So
Hmm.
uh, can we represent
Now,
this model as a single charge at a distance somewhere between, because the net effect is going to be between d and 2d, right? If is it possible to
you mean
represent this thing as a
so
single
so you
charge?
mean if you can put some single charge which has the same effect as to making the potential zero rather than using two image charges, something like that?
Yes, yes.
Yeah,
Representing both in the the
but I don't know how
the
to do that.
original
Like,
thing and the imaginary thing.
see, you cannot put any charges in this region. You want to find the potential here, so you cannot change anything here. Okay, now here what you can do is you can have some other combinations of, you can try to have some other combination of charges. I don't know what exactly, but you in like technically you can have some charge distribution that makes the potential zero on the surface. Okay, but this is the easiest way of defining image charges if you have some given distribution like this. But now the question is not to, so like whenever you have this, you can make use of the symmetry and This is the easiest way of having image charges so that the potential on the XY plane is 0. Okay. Because this makes use of the symmetry. Otherwise, you can have some other combinations, but that I don't think will be simpler than this. But the question is that suppose this is your charge, and this is some known image charge which you can think of just by looking at the system, right? From symmetry, it comes directly. So now you have these two charges and these two image charges. We want to find the electrostatic potential at some later points. So basically, you have some collection of charges now, right? And you want to find electrostatic potential at some larger distance. So what I want to make the point is that when you have such kind of charge distributions, think of the multiple expansion that we thought of, okay? Because now you have charge distribution, so there are discrete charges. There would be like you can take it as pairs, you can take it as individuals, and together they'll have certain impact and certain net potential, right? So the systematic way of dealing with it is to think of multiple expansions and look at how the monopole, dipole, and and the other higher terms look like. Okay. So in this case, obviously, because it's image charges which balance each other out, so the monopole term will obviously be 0, right? It's minus q plus 3q minus 3q plus q. So the net monopole term is 0 because net charge of this entire distribution is 0. But now the dipole term, whether that survives or not, how do you do that? So you have to find the dipole moments for each of these charges. And do you remember how, suppose if this is how the charges are distributed, how do you find the dipole moment of the system? So if you can find the dipole moment, you can actually find the potential because of that dipole moment. Okay, and see that if that survives. So if that survives, then that is the dominating term. You don't have to go to other higher terms because those will gradually be of diminishing magnitude. But if that becomes 0, then you have to go to the quadruple terms and think of the higher order terms, right? So in order to find the dipole moment of some given discrete charge distribution like this, how do you find the dipole moment? Do you remember that? Anybody?
I don't know.
Okay. So let us recall, right? This is something we have discussed previously. So let us recall. So when you have some charge, okay, and what is dipole moment basically? It's charge into some length, some distance, right? So how do you find dipole moment for this charge? You have this charge magnitude and you have a position, uh, position coordinate for this, right? Some position vector for this charge that is given as dz cap, right? So the dipole moment for this charge will be 3q into d z cap. Dipole moments are vector quantities. Similarly, for this charge, what will that be? It will be minus q into 2d z cap, right? Similarly here, you can find the corresponding dipole moments. And then you can add them and see if you have a net dipole moment. So can you tell me if we have a net dipole moment? So basically when you have discrete, so even if you have a continuous charge, what you do is then you do an integral of rho with the corresponding distances or the position coordinates of the charge element. Here you have a discrete charge. So what you do is you multiply the magnitude of the charge with the direction position vector. Okay. So can you see if we have a net dipole moment for this system?
Yes, there should be some net dipole moment.
Right. And what should that be? Just write the terms. So it's like 3q d z cap plus minus 2qd.
2QD Z cap.
That's the total, right?
Yes.
Okay. So now that means the monopole term is 0 and the dipole term is like these are the 4 terms each for each of these charges. So this is the final dipole moment that you get for the entire charge distribution. So as you can see that the dipole term survives, right? You have a net dipole moment for the system. Now what would be the expression for potential? If you know P, the dipole moment, how does the potential look like at longer distances? Because it said Z is much greater than D, right? So for a point dipole, suppose, how do you define the the potential at some distance R?
Dipole moment upon 4 pi epsilon naught r square.
Okay, P dot R cap, right? P dot R cap. So 1 by
P
4
dot
pi
r
epsilon
cap.
0, right? P dot R cap by R square. So here, obviously, it's all along Z. So this is how it turns out to be. Somewhere, if it has some component, then it have a cos theta component coming up there. Okay. So this is your potential that this charge configuration should have at larger distances. So basically, there are two concepts that we have used in this question. First is you had some conducting grounded surface and then you had some charge distribution. So obviously these charges would induce some charge on the conducting plate, but we don't know that. So what we thought is let us mimic that situation by replacing it with the image charges. Okay, so now you know whatever charges like it's the same condition. Okay, but a simpler version of it where you now know the charges. So this is the concept of image charges that we first used. The second thing that we used is that now you have some discrete charge distribution, and then you have used the concept of multipole expansion and looking at monopole, dipole, and suppose dipole was 0, then you would have to look for the quadrupole terms. So in this way, if you have some random charge distribution, you can try to find the potential at some distance where at some given distance. Here Z was much greater than R, so you can consider it as a dipole, a point dipole, and use this relation, right? So these two concepts. So this is how all that we are learning are actually interconnected. So when you're trying to solve the questions, try to think of all the concepts that you actually know and try to look at the easiest possible way of addressing the question. Okay. Okay, now this is another new section. So this magnetostatics. So I saw some questions on this in your assignments, which are quite trivial. But so to give an introduction, we saw that stationary charges result in constant electric fields. And the study of constant electric fields and this concept, this entire phenomena is electrostatics. Now, steady currents can result in constant magnetic field, and that is what is called magnetostatics. Okay. And if you have some steady current carrying wire, okay, along which moves, so some wire, okay, and the current is flowing, steady current is flowing along this wire, some random shape, okay, and then if you want to find the magnetic field that is generated because of this current at some point R, this is how it looks like. So this is called the Biot-Savart's law. And you can use this formula to get to this expression. So this is what is the current due to an infinite current carrying wire. Yeah, field due to an infinite current carrying wire. Okay. So what basically is done here is that you take some line element. Okay. So you have to find the distance from this line element along the wire to the field point that is given as R. Okay. And this is some trigonometric simplification. So it's like dl prime sine alpha. Alpha is this angle is also equal to dl prime cos theta. Okay. So theta is the angle that this end subtends at the field point. Okay. And similarly, you can also replace dl prime by s and theta. So if you do that, finally you can use this relation. Okay. Where now depending on the length of your wire, your angle that it subtends at the point P will vary. So for some theta 1 and theta 2, this is how it would look like for some finite segment of wire. And now if it is infinite, theta 1 will be minus pi by 2, theta 2 will be pi by 2. So if you put that value, you get this famous expression of magnetic field due to an infinite current carrying wire, okay, at a distance s from the wire. Okay, and the directions will obviously be given by this cross product. So if so there are certain questions in your assignments which are mostly based on this formula and this concept. So depending on which direction your current carrying like current is and your field point is, that is r, the cross product of that will give you the direction of the field. Okay, so now suppose if you have some square loop through which current is flowing. Okay, so can you tell me what, like just by looking at it, what the direction of the uh, field will be? So suppose if you take this line, you see that the current is flowing along, suppose x, right? And your field point is along y. So suppose x and y. So this is your current carrying wire, okay? And your field point is somewhere here. So if you use this thumb rule, so like what you see is your field is actually directed in this direction, right? Similarly, for this part of the loop, it will also be directed like this, right? So for all of them, you have the field directed upwards, okay? And how do you find the field? Obviously, so here now you have to look at, so each of these four sections, right? So what you do is first you just take this section, and here you would use this formula, right? So use this formula, and you know what is theta 1 and theta 2. So it should be 45 and minus 45, because this makes a 90-degree between them. So if you draw a line joining this and this, so the angle subtended there will be 45. So from there you find the field due to one such segment, and then you have four such segments. So if you do that, you find the net magnetic field, right? So this is how you calculate fields for different kinds of current carrying wires and different geometries. Okay, so now you have something like this. So can you try to solve for this question based on what you know? So you have to find the field here. So what's the first thing that one can do? Like looking at this question, you want to find the field here. So the first thing that one can do is find the contribution for this wire, find the contribution for this wire, and find the contribution for this semicircle, right? And then add that up. So what should be the contribution for this wire? So the distance between these two is r, right? So it's quite easy to evaluate. You have to use this relation, right? It's similar to having an infinite wire. But one thing is there, so the angle it subtends, that would be different, right? So here you are at this terminal, so the angle here that it would subtend would be 0, and another would be 90.
Both were direction is downward.
Sorry.
Both wire magnetic field direction, downward direction.
Magnetic field direction for both the wires are
Both the
same,
wire.
are same, right? Because the currents are at opposite directions. So if this is the direction, it's pointing downwards. If this is the direction, even here it's pointing downwards. So basically, see, this is for the for a spherical loop. So that's for this part of the section. Okay. So what it does is for some z, which is at some height. So here the field point is at some height from the loop. For our case, z would be 0 because we are at the same plane. So if you put that, you find mu0 I by 2r, right? And now you have half of it. So it should be mu0 I by 4r. So that's the contribution coming from this semicircular loop. And now you have this two infinitely reaching wires. So it's infinite at one end. So if you use that, okay, you get this. These are two half lines. Okay. And if you add the contributions of both of them, you would be getting something like this. So basically, you can break your segments into simpler segments and try to find the field. So here you'll be using the same expression as here for the wires. Okay. And the current directions, because the current directions are reversed here, actually the field direction remains same for both of these infinite wires. And even for this semicircular loop, you can try to see how so if the current is flowing along this, the field directions are pointing downwards. So this is the net magnetic field that one can expect for this geometry. Okay. So there could be numerous such questions. You can look at Griffiths or any standard book, and there'll be numerous questions like this. And another thing is that for image charges, you can look at a YouTube video by H.C. Verma, which he very nicely explains about image charges and how that can be used for, um, you know, potential calculations and things like that. So I think there are two such YouTube videos, part 1, part 2, something like that, and those are pretty good. So you can look at that. Okay. So now I would come to this section where there was this confusion in the in last class where someone asked me about, so if you have some capacitor in series combination, how are the charges getting distributed and how can we get to the final expression for capacitance? Okay. So this is how it happens. So suppose if you have some battery something and which is providing some charge to the capacitors. Okay. So this is a positive end. So it sends plus Q charge here and there's a minus Q charge on this end. Okay. So now when you have the plus Q charge here, this plus Q will be distributed in the surface that is facing the capacitor. Okay. So you'll have a plus Q charge along this surface, right? And this would induce a minus Q charge on this inner surface of this plate. Now, the question that I think the doubt that lied was, how is this minus Q again resulting in a plus Q here on this adjacent capacitor? And the fact is that is as written here. So when you connect, so see, these terminals are connected, right? So when you have this minus Q charge that is developed in this inner surface of this plate, how are we getting that minus Q charge? Is basically you are taking up charge from this plate, and that makes this plate positively charged. Okay. Similarly, because of this positively charged plate, you again have an induced minus Q charge here, which is achieved by taking up charge from this end. And this end we already know is at minus Q charge, which comes from the negative terminal of the battery. Okay. So if you look at this now, all of the capacitors have the same charge, which is Q, right? But they have different capacitance, and based on this capacitance, they'll have different potentials. So if you use that relation, you can see that you actually directly get to this expression for equivalent capacitance when in series. So is this clear? Okay. And another thing that we ended up discussing last time, and there was some confusion, was this, that so we initially had some parallel plate capacitor and there was some dielectric in between. And then when the capacitor was fully charged, the battery was disconnected and the dielectric was removed. And we saw that the stored energy increased. So the question was that where did this increase in energy, like this surplus energy, come from? So the answer is this, that the dielectric, obviously, see, there will be some induced charges on both inner surfaces of the dielectric, right? So as you will try to remove the dielectric, you actually, like, there'll be some work done. You have to do some work to pull the dielectric out. And that work will actually show up as an increase in energy, which would be stored in the capacitor. So, is this part clear? I think last time I was not able to explain it properly. I think it was Lakshmi, or I don't remember who asked me this question. So because of the charges on the two plates, there'll be some induced charges on the inner surfaces of the dielectrics. And so they'll be attracted to each other. Now, as you move the dielectric out, you have to do some work against this attractive forces. Okay, and that uh, results in this extra charge that comes up. So is this making sense? I'm not sure whether you're understanding, but okay. So basically that was it. So now if you have some doubts, you can ask me. Okay. So if not, let's call it a day. Okay. 1 second. Okay. So thank you.
Thank you.
Thank you. Thank you.